Hello, I'm Rohan Sarkar. In our paper, we introduce a new dataset that captures household objects with state changes, where the physical configuration of the objects change due to everyday interaction. This dataset can be used for fine-grained invariant recognition and retrieval tasks across different states. Our work has two major contributions. First, we introduce a new dataset that captures complex state changes in addition to pose and viewpoint variations. We introduce a curriculum learning-based mining strategy that helps in learning fine-grained state-invariant object representations, improving performance on object-level tasks significantly on our dataset as well as three other multi-view datasets. In our dataset, we capture complex state changes along with variations in viewpoint, pose, lighting, background of 406 objects across 21 categories. This includes visually similar objects as shown in the figure for fine-grained tasks. We collect 13837 images from arbitrary viewpoints in diverse state changes and other transformations. For each object, we provide category, object labels, and a text description. Our dataset has two splits. The first one is for evaluating state invariance and the other for testing generalizability to novel objects. The first SI split has 11,000 images of 331 objects split into training and test sets, which have no overlap with respect to the states of each object and is hence used to evaluate state invariance. The second GN split has 2.5 thousand images of 75 unseen objects that are not part of the SI split and is partitioned into a gallery and probe set and is used to test generalizability to unseen objects by correctly matching the probe images of an object with its gallery images. We extend a state-of-the-art pose invariance method Pyro that learns dual category and object embeddings from the images of an object pair that are randomly sampled from the same category. They use a dual encoder architecture with a shared CNN backbone and separate single-layer attention heads for each space to simultaneously learn category and object embeddings. It is trained using specialized ranking losses for each space. We use the same losses in our work. In the object space, the LPi object loss identifies confuser embeddings from the object pair and pushes them apart while pulling them closer to the multi-image embedding of each object. In the category space, we have one loss LPiCat that clusters images if the object pair is sampled from the same category. Otherwise, the other loss LCat pushes them apart in the category space. Due to state changes, there are large variations in an object's appearance across states, leading to high intraclass variance. Simultaneously, state changes can make instances of distinct objects from the same or different categories appear similar. Note that even objects from different categories such as tops, blankets, and towel may look identical when crumpled or folded. To deal with these challenges due to state changes, instead of randomly sampling from the same category like Pyro, we introduce a curriculum learning-based mining strategy that progressively samples harder object pairs based on inter-object distances in the learned embedding space, both from within and across categories. Secondly, instead of single-layer attention heads, we use multi-layer attention heads to capture invariance across complex state changes. In our mining strategy, we switch between three strategies. First, we randomly sample objects from the same category like Pyro, which may sample diverse object pairs from the same category. Next, we randomly sample similar objects from the same category by using approximate nearest neighbor to select a neighboring object from the same category. For S1 and S2, the joint loss is same as Pyro, which is the sum of all the object and category losses. Lastly, we randomly sample similar objects from any category by first partitioning the learned embedding space into Voronoi cells and randomly sampling object pairs from the same Voronoi cell. As training progresses, we split the embedding space into final partitions, thereby sampling harder objects from any category. For S3, the joint loss, we remove LPiCat that clusters images from the same category, as in this case, the object pairs can be from any category. We benchmark existing pose invariant methods on our dataset on 8 state invariant tasks on category and object level recognition and retrieval. Our approach yields superior classification and retrieval performance when averaged across all tasks on both the OWSC SI and GN splits as highlighted in yellow. The performance improvements are most significant for object level tasks as highlighted in green. In our ablation studies, we observed that these improvements are for two reasons. First, our curriculum learning-based mining is better at separating neighboring objects within and across categories than Pyro that separated randomly sampled object pairs only from the same category. Secondly, using two self-attention layers instead of one helps capture invariant features across more complex state changes beyond just pose changes. We observed that our curriculum learning approach also improves performance on object-level pose invariant tasks for three multi-view datasets, ModelNet, ObjectPy, and FG3D. The UMAP visualizations, where each object is shown in a different color, show that dual embedding methods on the right can better separate objects than simple embedding methods on the left that cannot effectively distinguish objects from the same category amid state changes. Comparing Pyro and our method on the right, we observe that the embeddings of different objects are much better separated using our method. Further, plot the intra and inter-object distances on the right, and from the inter-object distances indicated by the blue lines, we observe that our curriculum learning approach leads to better separation, resulting in improved performance on object-level tasks. We show that our method can accurately retrieve images of the same object under different state changes on the left and distinguish between similar objects shown in consecutive rows on the right, such as blue bags and red tops, and accurately retrieve the images of the correct objects. In conclusion, we present a novel dataset that captures state change of objects that is useful for several real-world applications and can be used for evaluating fine-grained invariant recognition and retrieval. Lastly, we introduce a curriculum learning-based mining strategy for fine-grained tasks.